This is Richard Walker from Lucidate. In this video, we will look at some of the mathematics that underpin popular AI methods. We'll examine neural networks, a popular artificial intelligence technique for classification problems. This includes computer vision, where we're able to identify and classify objects based on pixel intensity. In this video, we're going to look at multivariate calculus. People might hope that after leaving school, they would never have to come across calculus again. We're going to solve some daunting equations. These equations. To many people, they look complicated, but the results aren't complicated. Not at all. When we work out the derivatives, the answers turn out to be trivial. The individual components of our solution boil down to be one of four things: either 0 or 1, the input weights for a neuron, the input activations for a neuron, the difference between the answer we expect and the answer we got. So, all this apparent complexity of these formulae reduces to a binary number, two scalars, and a subtraction. Keeping this simplicity in mind is useful if some of the maths gets daunting. To recap from the previous video, we have 28 by 28 pixel images of clothes. So we have 784 inputs for each image. Each input has a grayscale number from 0, black, to 255, white. We have 10 different types of image. This gives us a good start in constructing our network. Our solution will have 784 inputs, numbers that vary from 0 to 255. Likewise, we can propose 10 output neurons. Each output neuron handles one specific item of clothing. It will have a high activation if the network predicts this particular garment, a low value otherwise. We've looked at a popular AI approach to classification, neural networks. These contain simple processing units stacked into layers, the outputs of one layer feeding the neurons in the next layer. There are lots of definitions of neural networks. For now, I'm going to describe them as a crazily complicated function made up of simple processing units with a vast amount of parameters. A network with 784 inputs, 10 outputs, and 2 hidden layers of 128 and 64 neurons is small, certainly small by AI standards, but this small network will have 109,386 parameters to tweak. You might recall simple functions from school that look like this. This function takes one input and has 3 parameters. But our input can't even fit on a screen. A neural network is a function, but a big one, and there's a lot going on inside. As soon as we see that things have a vast amount of parameters and are crazily complicated, most of us will be tempted to give up. But we can figure out a way to delegate the crazily complicated, vast parameter stuff to a computer. Computers are frankly indifferent to large, complicated data sets. The trick here is to get the computer to pick the best set of parameters that solve the crazy complicated function. It's quite clever, but also simple, elegant, and intuitive. A card trick can look mystifying until you know how. So it is with artificial intelligence. Let's take a look at how we can unpack this problem. We'll lean on the calculus concepts we introduced in the prior video. We'll take a simple example and apply some more formal mathematics to our gradient descent intuition. We have a 28 by 28 grayscale image of a bag, a set of 784 numbers that represent the pixel intensity of the image. We can feed this into our network. Then the network takes over. It multiplies weights, adds biases, and feeds the first layer. Neurons in this layer become active. Their level of activation is determined by inputs, weights, biases, and that neuron's activation function. This process continues all the way to the activations of our output layer. we can compare the actual output activations to what we want to see. What we want is an output layer with 9 zeros and 1 1. The 1 will represent the specific item of clothing in this test sample, the bag. We want to minimize the cost function and get our actual output as close to the desired output as possible. If we look at the neuron that looks for this item of clothing, the 5th, we would like that to be 1. This means increasing its biases and weights. Also, we'd like to increase the activations of the hidden layer. If we take one of the other output neurons, the 1st, that we want to be 0, we can see that we want to nudge its activation down from 0.8 to 0. That will mean that we want to nudge the bias down, and we'll also want to nudge all the weights down. If we could, we'd also like to nudge the activations of all the neurons in the final layer down. We can't do this directly, of course. These are the results of calculations that happen further upstream in the network. But this is just one training example. We need to show other items of clothing to be able to optimize the weights. Let's take the example of an ankle boot. Again, we input the 784 grayscale pixels of the image as our activations of the input layer of the network. Each neuron becomes activated according to its inputs, weights, biases, and activation function. Here the output is closer to what we want to see, with a mean squared error of 1.69. We want to nudge the activation of the first neuron in the output layer up a little. The rest of the activations need to be nudged down, with the biggest shift being necessary for neuron 4. So far, for each training image, we've seen which direction we want to nudge the weights and biases. We've also seen which direction we would like the activation of the previous layer's neurons to head. But by how much? Well, to figure that out, let's return to the example of the bag. When presented with this image, you'll recall that we want to increase activation 5. In this case, from 0.2 to 1.0. Nudging up weights and biases will help us minimize the mean squared error here. If we write down our cost function, it's the square of the error between our desired output and our actual output. For this example, it's 2.54. As we've observed, we'd like the activation of neuron 5 to increase. At the same time, we'd like a decrease in all the other neurons. To do that, we must alter the parameters of the network. We can nudge and shift the weights and biases to achieve this. We can see that we want to increase the bias of the 5th neuron. That can only increase its activation. We'd also like to nudge the weights up to increase the activation and lower the cost function. The changes to weights connected to the 4th, 8th, 12th and 14th neuron in the last hidden layer are the most sensitive. They'll have a greater impact on minimizing the cost function for this sample. This is because the activations that these weights modify in the penultimate layer are large. While we can't directly change the activations in the hidden layer, we have a greater impact on minimizing the cost function by nudging the activations that are connected via the larger weights. This is important. Let's make a note of that observation. We want to increase the bias in proportion to the error, 1. Change the weights in proportion to the activations and the error, 2. And change the previous layer's activations in proportion to the error and the weights, 3. If we now look at neuron 1, we see we want to decrease the activation to 0. Same logic, different direction. The bias wants to go down. The weights want to decrease. The weights with the biggest sensitivity will be the ones connected to the most active neurons in the previous layer. And if we could, we'd like to reduce the activations in the previous layer. Again, the activations with the biggest impact in reducing the cost function will be those connected via the biggest weights. Now, this is just one example. Let's look at others. Here we have an ankle boot, a shirt, and a sandal besides the bag. Each will have their own result. Each result will generate its own cost function, and each will have its own influence on the change to the weights and biases. The more training examples you have, the better. In the next few videos, we'll train some neural networks using tens of thousands of labelled images. Frankly, there's no way around this. The more training data you have, the better your AI will be. As we train our network, there will be lots and lots of conflicts and lots of contradictory nudges to our parameters. At first, these conflicts will be large, but as the network sees more and more samples, things will settle down. The tweaks and nudges will be quite small. This is usually referred to as learning. So now we're at the final technical bit. Here we determine precisely what each nudge and tweak should be in response to each training sample. We'll introduce and name some variables. That way we can write down some equations and keep track of what the maths is telling us. Recalling we have a network with 784 inputs, we have 10 outputs and also 2 hidden layers. The activation of each neuron is just a number. We can stack the activations of each layer into a vector. Our input vector represents the 784 grayscale values. We'll name a vector AH1 to hold the 128 activations in our first hidden layer. Similarly, AH2 will hold the 64 activations in our second hidden layer, and AO will be our output vector. Each of the neurons in our hidden layers and our output layer will have weights. We can use a rank 3 tensor or 3D matrix to hold these weights. The weights connecting each neuron in AH1 to the input layer can be stored in a matrix called WI. The weights connecting the neurons in the second hidden layer to the first hidden layer are stored in a matrix called WH1. And the weights of the output layer are labelled WH2. For clarity, let's restate. Every activation and every weight is just a number. For convenience, we can stack all the activations in a layer together in a vector and give it a name. Here with a superscript. Each of the 10 neurons in the output layer is connected to every one of the 64 neurons in the final hidden layer. Each of these weights can be conveniently represented in a 64 by 10 matrix. Other matrices represent the larger number of connections between the other layers. These matrices can each be named and can be stacked together as an order 3 tensor. Every neuron will also have a bias. Just like our activations, these can be stored in a vector. Let's use our familiar example of the bag. How do we nudge the weights and biases to get a better answer for this training example? In which direction and by how much? Before we start, we need to restate 2 rules from calculus. The first is that the derivative of a vector is the derivative of each element of a vector. Secondly, if we have a composite function, a function of a function of a function, then we need to apply the chain rule to get the partial derivative with respect to any input. With that in mind, let's look at the sensitivity of a neuron's activation. This neuron will receive inputs. These inputs are multiplied by weights. We sum this product and add a bias. The result is then fed to our activation function. For this example, we'll use a ReLU. The activation is therefore sensitive to 1. the inputs, 2. its weights, 3. the bias, and finally its activation function. The weights and the activations are both vectors. The bias is a scalar. The calculation of the output is a function of a function. We first use a composition function, multiplying the inputs by the weights and adding the bias. We then feed this result into the activation function, the ReLU, to generate the output. We therefore need the simple vector rule that the derivative of a vector is a vector of derivatives, or apply the derivatives in parallel. And we need the slightly more complicated chain rule, apply the derivatives of each function in series. The sensitivity of the output to the bias, or expressed mathematically, the partial derivative of AO with respect to B, requires the chain rule. This partial derivative is the derivative of the output with respect to the activation multiplied by the derivative of the activation with respect to the bias. Said like that and written like this, it can seem complicated. Well, That's maths notation for you. The answer, though, isn't complicated. The answer is trivial. If you differentiate the activation function with respect to the bias, you get 1. When you differentiate the output with respect to the activation function, you get 0 or 1, depending on whether the bias is exceeded or not. You may now see why the choice of ReLU is such a popular one. Among many other attractive properties, it does make the calculation of derivatives pretty straightforward. The sensitivity of the output to the weights also uses the chain rule. It's the derivative of the output with respect to the activation function multiplied by the derivative of the activation function relative to the vector of weights. This comes out to be the vector A. That's to say the relevant activations from the previous layer. Again, multiplied by 0 or 1, depending on whether this neuron fires or not. Finally, we get a similar result for the last partial derivative. The sensitivity of the output to its inputs is simply the vector of weights. So, a lot of complex maths to get a very simple result. The sensitivity of the output to the bias is either 0 or 1. The sensitivity of the output to the weights is either 0 or the inputs. Finally, the sensitivity of the inputs is either 0 or the weights. Let's bring everything together and present the backpropagation algorithm. We'll put our notation, our work on derivatives, and our cost function in the margin on the screen as reminders, as well as our intuition regarding sensitivities. You'll recall that when we showed the bag to the untrained network, it did a lousy job. Right now, the most active neuron in the output layer is neuron 1. This means that the network thinks that this bag is an ankle boot. Let's see how we can use the cost function so that the network can bump its parameters in the right direction, enabling the network to do a better job. The output we want is zeros everywhere and a 1 in neuron 5. You'll see that we want to nudge neurons 1, 7 and 9 down a lot. For simplicity, we're going to focus just on neuron 5. The mass is the same for all the other neurons. Here, we're comparing two numbers, the fifth element of AO, our output, with the fifth element of Y, the correct label for this image. We can write out neuron 5's activation function in yellow. It takes all the inputs from the previous hidden layer. This is AH2. It then multiplies these activations with the weights from the fifth row of WH2. It sums these up, adds a bias, and pumps the result through the ReLU. One last time, let's recall the vector rule and the chain rule. Let's take our cost function from our marginal notes on the bottom left. The full cost function is shown here. If we want to look at the contribution of just the fifth neuron, we can write out our cost function like this. The cost is a function of a function of a function. First function is composition. Sum the product of the weights and activations and add the bias. The second function is activation. Apply the ReLU. These are exactly the same operations we saw when we were looking at the activation sensitivity earlier on. The difference here is we have a third function. This takes the square of the difference between our observation and the actual result. We thus expect that the chain rule would give us a very similar set of derivatives to our previous example, with the addition of an extra term for the square of the error. So, to get the sensitivity of the cost function to the parameters, we'll need three derivatives, one for each of the bias, the weights, and the activations. We can go through the same logic as we went through with the activation sensitivities. As with the prior exercise, the notation can look daunting, but the results are simple. The good news here, it's the simple results that you need to remember, not the notation and derivation. So, let's start with the sensitivity of the cost function with respect to the bias in the fifth neuron. The chain rule tells us that the sensitivity is 1, the sensitivity of the cost function to the activation function, multiplied by 2, the sensitivity of the activation function to the composition function, multiplied by 3, the sensitivity of the activation function to the bias. As before, these equations can look menacing. Too many Greek letters, too many indices in subscripts and superscripts. But as before, the solutions are simple. The first equation in the chain rule is the activation of the fifth neuron, what we got, minus the expected activation, what we want, squared. the partial derivative is 2 times that difference. The second equation in the chain rule is the one we've already seen. It's the derivative of our activation function with respect to the composition function. For a relo activation, we know that this comes out to be either 0 or 1. The final equation is also familiar to us from our work before. It's the sensitivity of the composition function to the bias. The bias is not raised to any power, nor is it multiplied by any coefficient in this function. Thus, we know the derivative is 1. For the sensitivity to the weights, the chain rule tells us that the first 2 partial derivatives are the same. These are the sensitivities of the cos function to the activation function and the activation function to the composition function. So we can just write these down straight away. The final derivative is different. This is the sensitivity of the composition function to the weights. Here the weights are multiplied by the activations, so the derivative is simply the activation vector. The final term is the sensitivity with respect to the activations in the hidden layer. Again, the first 2 terms in the chain rule are the same. The sensitivity of the composition function to the activation functions is just the weights. This is a really elegant result, and this is where the term backpropagation comes in. We clearly can't modify the activations in the hidden layer directly, but we know from this equation how much we would like them to change based on this training example. Now, this is exactly the same situation that we have in our output layer. We know how much we want to change the activation. The elegant thing about this result is it doesn't just tell us how much to change the parameters for the final layer. We can apply this recursively up the network from back to front to tell us how much we need to change all the parameters. Very elegant indeed. Again, the derivation looks complicated, but the results are simple. They also align with our intuition from earlier, that we move the bias based on the error. We move the weights based on the error and the activations, and elegantly, using backpropagation, we have a goal in mind for changing the activations based on the error and the weights. Thank you for making it to the end of a longer than usual video. Some of the maths got detailed, but here the details were only important to explain the derivation. It's not important to remember all the details of every derivative equation. What is important is that you know there's no magic or voodoo involved in a neural network learning. It just uses some very simple derivative results to come up with an optimal set of tweaks. In practice, to speed up training, you don't show every single training example for every learning iteration. You shuffle up the training images into a mini batch and use this subset. If the population of the mini batch is diverse, you lose very little in precision and gain a lot in speed. Also, you can control a learning rate, a simple scalar number applied to the derivative to stop the algorithm overshooting. And that's it. This is Richard Walker from Lucidate. Join me in the next video when we put this into practice and get the computer to recognize and classify images.